Hi, everyone. Welcome to PayPal. We are really excited to host the inaugural Go meetup in South Bay. And my name is Aarti Parikh. I've been working in Go for a few years, and I love the community. And when I started in PayPal, I was like, Go is coming to PayPal. I gotta make it happen. The fun stuff here that I saw in SF. So a couple of things I like to start in all my meetups is, who's looking for a job? Please raise your hand. Cool. And who's hiring? Please raise your hand. The guy in the back, Rajiv, he's my co-organizer. He's hiring. Talk to him. One more thing, administrative. We have a code of conduct, just like Golang, and we follow that. So if you have any issues, just talk to me or Rajiv. I think it should be fine, but just in case. So our first speaker is going to be Bala Natarajan. He's the Director of Engineering for Build and Test Platforms. He's also the reviewer of the GoPL book, which you all might have read, which I discovered after I joined PayPal. I was like, oh my gosh, he reviewed that book. So without further ado, Bala Natarajan.
Thanks, Aarti. One of the problems with Aarti is she tries to publicly shame me like this. I used to be smart, not anymore. Okay. First, a warm welcome to all of you who have come here for the inaugural edition of the Go Silicon Valley meetup. It's been a long-standing want or need for us that we need something in the South Bay. And we found out that GoSF gets all the credit. They get the best people to come and talk. It's just that it takes 5 hours for me to go and come back. If I look at the graph of the number of times I've visited, 2015, I attended a lot of meetups, including the 2015 December meetup at Facebook, the Gopher Fest. And then 2016, it started falling down. 2017, I hardly attended any. And like 2018, when Aarti came on board, I was super happy that we could organize something within South Bay. And she was like gung-ho about organizing here. And thanks to my team who had pulled off a lot of work in organizing this, because this is the first time we are doing it in the South Bay. And we are also trying to get things organized. So thank you very much for everyone who have given the long weekend and coming over here. Thank you. Again, a warm welcome. And I wanted to kind of quickly tell you who am I. I'm Bala Natarajan. As Aarti mentioned, I'm a Director of Engineering for the Build and Test platform, which is part of the developer experience. The developer experience at PayPal essentially focuses on the DevOps infrastructure. We enable the DevOps infrastructure for all of PayPal and PayPal Inc. As in any organization, we are good in tools. We also have a lot of investment in Google Cloud, AWS, and you have experts around my team as well as across the organization who understand these cloud technologies and stuff really, really well. And this is where Go fits in for us. My interests primarily rely on re-engineering large-scale systems. As opposed to engineering large-scale systems, I believe the complexity is re-engineering them. You have engineered, you have deployed a system. We deal with systems, some of my team members deal with systems that are 12 years old or 15 years old. Re-engineering them, redeploying them, and making them work in a large-scale environment has been a challenge. I have done that multiple times within PayPal. I've done that for the payment system. We were able to horizontally scale our payment system. We have done that for some of our identity subsystems. We have done that for our cloud. So it's, and the whole idea of this is that we'll be able to share some of what we learned with all of you, at the same time understanding what the industry is doing. So why GoSV? Driven by our needs, we don't have a good thriving community of Go developers as well as people, engineers who are interested in these topics. We don't have to essentially focus on Go, though that will be the primary motivation. It will be centered around everything around Go. We want to talk about distributed systems. We want to talk about clouds, native systems, cloud system, Google Cloud, and some topics that people don't talk about. How do we do fleet management? How do people handle large fleet sizes? Thousands of VMs, tens of thousands of containers. How do you deploy all these things neatly? And how do you optimize them? Not much is talked about how do we optimize. Auto-scaling is just one function that the cloud providers provide. How do you use them? How do you optimize your CPU usage? How do you optimize storage? How do you optimize for things like network bandwidth? How do you optimize for managed services? Like say, for example, Google provides a lot of capabilities to use BigQuery and stuff like that. How do you optimize their usage? How do you use Stackdriver, or how you built your own monitoring systems on top? So these are things that are very interesting for us. And it will also be awesome to get the community's insights on how they're engineering their systems. Again, my interest is in re-engineering. People have taken something from the data centers and how do they move it to the cloud, and what are the types of tools that they're deploying. So we believe this group would evolve into a time over a period of time to talk about all these problems at scale. And that's our vision for it. Future, all your submissions will come through papercall.io, and we will be advertising that as part of the GoSV, right? Yes, so we'll be the right place where we'll get all the insights. So please keep your participation. The most important part of anything is starting is easy. I would not to discount the work that Aarti and my team have done. Starting is easy, but maintaining the momentum is really, really, really hard. So we need your cooperation, your unfulfilling faith in ensuring that this GoSV meets your needs. So from that perspective, your help coming to these meetups, giving ideas on what it should be, all of them would be super, super, super valuable. Okay, some of us would be hanging around, and we can always after the meeting, after the meetup is over, we can always hang around, have conversations. We can go to a bar too if there is interest. Okay, thank you. So before I kind of walk off the stage and give the mic to my next speaker, I want to talk about why is Go interesting at PayPal. We like Go because there's code clarity. People talk about different things. We like its code clarity, lesser number of features interest us. Shipping binaries interest us. The security capabilities that you can do interest us. Interactions with, since our PayPal has been evolving, since our systems, many of you startups are in one end of the extreme. And as the organization evolves, your systems evolve, we find that there are tons and tons of network systems. How do you interact with network systems? Or systems of systems, which is where our interest is. Faster compilation. How do we compile faster? How do we ship things faster? So these are all the areas why Go has been very interesting for us. And Chris would be talking about, he's part of my team, and he talks about how he's moved some areas which are written in Python to be in Go. And that makes a classic, patterns that he has developed so that we can re-engineer systems over a period of time. Without further ado, I want to kind of thank some of the folks. Thanks to Aarti and my Rajiv, who have been primarily organizing, and Rajiv and his team who have pulled this all together. Thanks to my sponsors, my employer, PayPal, who have been more than happy to support us in starting this GoSV and giving us this room and ensuring that we have got everything done. So thank you very much. And thanks to all of you for coming over. Again, a warm welcome, and thank you very much for coming over for the inaugural edition, given the fact that we have only a shorter week, keeping aside your time, and thank you very much. We all owe a big one to you. Thank you.
So our next speaker is Sanjin Lee. He's a distinguished engineer at PayPal, leading the container and routing platform, former Twitter, and also runs the internal Go meetups at PayPal. So,
welcome. Just give me 1 second before I can. This is one downside of using Google Slides. It needs network. Oh, there we go. Okay, I'm super excited to have you here for the inaugural meetup for Go South Bay. Welcome, everyone. So let me talk about briefly, who I am first, and then I can talk about how we do Go here at PayPal. There are a number of very exciting and interesting things that are being done in Go. So let me go into them. So my name is again Sangjin. My Twitter handle is sjlee. Follow me, please. I look exactly the same as like 10 years ago, just like that. So I lead the container and routing platform team here at PayPal. So my job is in two different places. One is the container platform, as in you can think of things like Mesos, Kubernetes, and things like that. So we are actively working on migrating PayPal's production and QA environment into a container-based orchestration system. So that is one thing that our team is doing. And the other side is the routing platform. By routing, what I mean is layer 7 routing, not layer 4, layer 3, where we basically do routing based on HTTP and intelligent service-based routing. So that's the other part of what I do. So the reason I'm really passionate about Go is these two teams are actually heavily invested in Go. So we are actually one of the biggest investors in Go here at PayPal. So I'd like to just talk briefly about the things that we do. So for our container platform, our project is called Genesis. Genesis is basically multi-region container orchestration platform built on top of better known lower level container orchestrator like Mesos and Kubernetes. Today we are running on top of Mesos, but it's pluggable enough so that if we change our minds, we can actually move on to something on top of Kubernetes. But the value we are adding is really more about being able to deploy and fully leveraging multi-region, multi-deploy zone and things like that. We also added tons of value in terms of providing all the great user experience in terms of being able to control your deploy pattern and all kinds of different features that people really need when you really want to deploy very sophisticated production applications. We have multiple components that are really being written in Go. Our core, Genesis core, is in Go. And we also have something called DCE Go. That's a Docker Compose executor that's also written in Go. That's basically a way to spawn a set of containers, Mesos Docker containers for Mesos integration. And that's actually something that we developed purely in Go, and that's actually open source. So you can check out DC-Go in GitHub, and you'll find that that contribution that's already open source under the PayPal in GitHub. The second thing I can talk about is also something called Gorealis. Gorealis is basically our feature add-ons for Aurora. Aurora is basically a framework written on top of Mesos. And we actually had to add a number of features for Aurora. And this Gorealis library is a collection of those features that we wrote. That's also in Go. And finally, the last piece for Genesis is something called Milky Way. Milky Way is our contribution in terms of having a better container networking than the standard choices that are being provided, like the bridge networking and things of that nature. Actually, there's tons of very exciting innovations inside Milky Way. I cannot share all the details about Milky Way in this forum, but we are working hard to open source both Genesis and Milky Way in the months to come. Hopefully, sometime next year. I cannot really promise it, but we are working hard towards open sourcing both Genesis and Milky Way, and I can't wait to share exactly what they do in terms of their technology. So that is sort of the Genesis, the container platform part of our work that we're doing in Go. PayPal's next generation L7 router is called Stargate, and that is also being completely rewritten in Go. we actually have multiple generations of the L7 routers here at PayPal, ranging from C++ to Java-based L7 router, based on things like Netty and stuff like that. But we are in the middle of consolidating all those products into a single platform that's based in Go, and that's in active development. Again, our goal is to open source Stargate when it's ready. So you'll probably hear from us about Stargate pretty soon too. And then there are actually other things that are being worked on. PayPal has something called OCC. OCC is PayPal's database connection management platform. This is actually what enables PayPal to scale to really large-scale Oracle and database installations that we have today. And this is really one of our key innovations that we have at PayPal. And one of the core pieces in OCC is actually written in Go. Another piece is something called Juno. Juno is PayPal's key value store, and this is another new exciting product we're working on. And then actually there are tons of other monitoring tools, developer productivity tools that actually Paula touched on. There's tons of other exciting work going on that are all being done in Go. PayPal used to be really heavily on fairly legacy languages like C++ for a long time. And then PayPal actually made a transition to Java, JavaScript, basically Node, and also a little bit of Scala. So our current existing mainstream service languages are more like Java, Node, and Scala. But the interest in Go at PayPal is rising pretty rapidly. This didn't used to be the case at least a couple of years ago. I think in the past 1 year or two, the excitement and the interest in Go has been rising steadily and pretty rapidly in my mind. And a lot of the projects in the platform area and tools area are seriously considering Go and already working in Go. And the reasons are pretty along the same line as what Paula talked about earlier. The code clarity, ease of development, ease of learning curve, and really strong runtime performance, smaller resource footprint, and things like that. Those all contribute to a lot of exciting new work that's happening here in PayPal. Another interesting thing is that the interest is really growing organically. It's not like somebody came up and say mandated, you guys shall go start looking at Go today. That it never happened that way. I think this was really tremendously organic. People actually started dabbling in Go, started exploring ideas, did some POC work and things like that. And we began to latch onto the real strong possibility that this will work really well. And so far it has proven true for the most part. We're also in the process of consolidating all the common pieces for Go. So we're actually building what's called the Go framework, because there are these different products that we already use, but they share a lot of the common substrates. So we are actually also building that common framework so that people can really leverage each other's work. And we are really operating in a very much open source model, inner source model really, inside PayPal. So we actually are building this Go framework. And a lot of the Go people inside PayPal are very much dispositioned towards open source. So we like to open source as whenever we can. That's the disposition we have in the container and routing platform. I'm pretty sure. I don't know why I did that. Okay, I'm done anyway. So I'm pretty sure that you're going to see a lot more open source projects coming out of PayPal in the Go area. So I'm really excited about its future here at PayPal. Again, welcome and enjoy the meetup.
So someone asked about Wi-Fi password. It's safe payments, S capital, P capital. Next up is JBD from Google, who's going to teach us about tracing for granularity.
No, no, this is slightly different.
Hello, everybody. Thanks for coming. I'm JBD. I will talk about tracing and some of the upcoming features in Go 1.11. First of all, a little bit introduction about me. I'm using Go as a primary language for a long time now. I used to work on Go at Google for a while, and now I'm mainly focused on reliability, latency analysis, and debugging tools, specifically for distributed systems. So one more thing, I actually came directly from Cabo a couple of hours ago. So this was exactly where I was standing, and that's my luggage if you need the proof. So now I'm here. So this is how great this meetup is supposed to be, I guess. Let's go back to tracing. The title says tracing, and I want to start giving a little bit more idea of what tracing is, because it's such a umbrella term. And why do we trace? So you came here for Go, but I will give you pipes, because I think that pipes are the greatest analogy for anything related to systems. What you're looking at is pipes, specifically water pipes, and these are the connectors of different components. If you want to transfer some water from one place to another, you're using a pipe. Have you ever thought about the availability of a pipe network like this? How would you measure it? To begin with, actually, let's ask, what is the availability of a system? If the whole purpose of the system is to move water from one place to the other, can we just say, it's about how much water we are carrying, or how efficiently we are transporting water from one place to another? I just want to remind you that this talk, or tracing in general, is not just about performance. As a disclaimer, I'm talking about availability, and we just want to get the basic things going on and understand what is going on when there is something wrong, for debugging purposes. So I want to make it clear that this is not about performance, but understanding the availability and debugging if there's a problem. So there are various factors that may affect the availability of the system. For example, if there's a pipe clogged, it's not going to work as expected. Or if there's a pipe that is leaking and not pressurized enough, we will not get the same throughput from the system. Or, and also, what is the path and direction of the water, right? Until the water is served at the endpoint. We can easily diagnose what is going wrong, and what are the components that are involved in the outage by answering this question, if we have this understanding. So, what if the water is just leaving some hints behind as it's flowing through these pipes? So we can just generate the flow by looking at those prints. Tracing allows, to see things end to end until we serve what we want to serve to our users. It can be water, just like in this case, or it could be a function call or an HTTP request. The basic principle is the same. You trace subcomponents to see what is happening end to end, and see the impact on the user. So we, as an industry, have this, usually use a very, trivial numeric value when we're talking about availability and move on. But how practical it is? For example, 100% availability. it's unfortunately a lie. There's no 100% availability. In any system, it's so complex to achieve 100% that we typically just don't care about it. Then what is good availability if 100% is what exactly not we're trying to achieve? Maybe we should first ask, what's availability? We have this sort of definition that availability is about whether a service is performing as the user expects or not. If availability is just like giving user the experience that there is no outage actually. So if they're not looking at the service and if there was an outage, we can. The point here is to user's perspective. If we're having an outage when the user is not looking at it, it's not an outage in this definition. So failure can happen, but it should be rare enough. And it depends on the business case. It depends on how much failure your users can tolerate. But the key here is the goal is not 100% because it's a waste of resources. So your team usually have to have a more principled way of saying what is available to it. And how much downtime is acceptable. At Google, we have this concept, a methodology to define and use availability principles all across the org. We call them service level objectives, or SLOs for short. There are two major categories we're interested in. The first one is the acceptable error rate for any service. The second one is the latency boundaries. We usually set something like, hey, 99.99 of all the requests should be responded in under 100 milliseconds. So, and it's, again, we are never setting this boundary for 100%. It's usually the 99.99. And similarly, we set some throughput expectation if it's a background job, such as a job that reads from a queue, does some processing. What matters there is more about throughput rather than the latency. So tracing can be done, in a single process, or it could be distributed among multiple processes. This is an example trace, a visualization. You're currently looking at a distributed trace, and there you can. This is at the request or RPC level. What user is experiencing here is this 300-ish milliseconds of latency. But as the operator of the system, if we have distributed tracing around, we can actually see what happened in that 300-ish milliseconds. It looks like we are, jumping among multiple services until we respond. So the user is first getting slash messages endpoint, and internally it requires 4 other calls. Each yellow box here is actually representing an RPC call. First, we check the integrity of the request, the first box, and then we make sure the user is authenticated, and we do some cache up, and I think it's a cache miss. We go to Spanner and query the result. And you can see how long it took for each subcomponent to respond, and more importantly, what components were required to respond to this request. So this is what tracing instrumentation and visualization gives us. And this is another case. Here in this case, we have this 245 milliseconds, but the customer is on the phone maybe calling us right now like, hey, this API is not responding. It just responds with an HTTP 500 and there's no other error message. We can, again, as the operator, we can take a look at the distributed trace and see what happens, because internally we collect more details usually. It looks like we were sending a malformed payload to the cache service. That's why the cache lookup is failing, and it fails the entire endpoint. So we can fix this bug. There was a bug in the code. We just ended up in a edge case sending this malformed payload. We can fix that and then redeploy, and things are going to work. So this is exactly what happened when I first joined Google. On my first day, somebody showed me our distributed tracing system and assigned me a bug. Hey, can you just take a look, try to reproduce? And I was able to see, it was failing because of a payload issue. And I fixed it, and I think on my first week I had something in production, which was insane. So I want to talk a little bit about latency, because we said like there are two critical measures. The first one we were talking about was the error rate, which is usually very easy to understand and easy to debug. The latency issues are a little bit harder. So what we benefit a lot from tracing is, underlying the underlying causes, understanding the underlying causes when it comes to latency. So what causes latency? That's a tough question. Who knows? Like too many moving parts. Network outages, scheduling problems, like poor utilization, GCP, GC, GCP as well. For me, it's GCP. Computationally expensive code, right? Like you're burning a lot of CPU sometimes just because you rolled a new compression library or something. It's hard to pinpoint. So Go has become this language, de facto language to write servers nowadays. It's yay, we're celebrating a lot, but at the same time, we have some particular problems because most of our users are writing servers, and the particular issue with the servers is there are tons of independent requests going through a server. And they're interacting with a bunch of things like common components and runtime. So it's affecting the overall state of the things. So they're not that independent. You're tweaking the runtime, so you're affecting the state of and the health and the availability of the common components. So the activities that are occurring during the program execution that we usually want to understand more is, scheduling, memory allocation, garbage collection. But it's very hard currently to associate a single request with its impact on the runtime, and to understand, what is also runtime's impact on a particular request. So if I go back to the pipe analogy for a second, by using for distributed tracing, we said that we can narrow down, hey, there's a latency issue at the server, at this maybe RPC. But it doesn't give us any further understanding. We still need to go back and see sometimes the source code, understand what else is going on. If a pipe is clogged because of a runtime event, it's hard to understand the case. And maybe address it with an optimization. It's especially, a critical issue if it's something repeating. Sometimes an RPC is just repeatingly, there's more of a latency issue with a server or one RPC handler. And this is not very easy to replicate, or reproduce locally during development time because, the behavioral patterns, the load, the high load is sometimes the reason why a handler is suffering from some latency because, GC is happening. So this is one of the common feedbacks we get from our SRE. They usually say that, hey, there's no easy way to say why latency is so high for, some requests. Is it garbage collection, scheduling, or some blocking syscalls? Can you please review and, advise us what an optimization could be? So nobody on the earth can actually, read the code and understand and digest all those lines and, understand the complex relationships and, tell them to optimize. We need actually a better diagnostic solution. So I want to enter the world of the Go execution tracer. This tool has been around for a very long time. It's been contributed by Dimitri Yukio. It's the current de facto tool to diagnose Go runtime. He contributed this tool because he was rewriting the scheduler. He needed a tool to understand his rewrite. It currently reports fine-grained runtime events from a Go routine, and it reports the utilization of CPU cores. But it cannot tell what specific user code is associated with those events. So under high load, there's so much going on a server that it's practically not very easy to isolate a case and understand the problem. by looking at the output of this tool. So I will go back to the previous distributed trace, and I want to focus on this like second call out access token. So assume this 172 milliseconds is an unusual latency. We can see this from our metric collection. We can collect metrics for this endpoint, and it may violate our SLO and give us an alert that hey, there's this like unusual latency. And then we can take a look and try to figure out what is going on. So we first usually check like, hey, there's no host-related specific or network-specific incidents affecting this service. So we need more data maybe from the runtime to see what is going on. So the execution tracer is adding this new feature that allows us to mark sections in the code. Then we can simply break down how much time is spent on all these different sections during the execution. Access token handler is in the second line. You can see that it's executed and preempt, executed and preempt. These little transparent boxes are representing that. And with 1.11, the execution tracer will now be able to generate a report where the time is spent on those boxes. What you see here, first we did some networking. We actually did some networking in that box, 6 to 8 microseconds, and then we executed the handler. Probably it's for serialization to serialization, 123 microseconds, and then we waited on some blocking syscalls. This is not the order of the things. This is more about the final summary. And then we also spent some 8 microseconds for garbage collection, just when we were executing that little transparent box. And we have data for all the transparent boxes. So execution tracer is not just going to report the latency details. You should be also able to visualize the overall flow. In the other visualization, we see that the purple boxes here are where the handler is being executed. So it's been momentarily blocked, and then it was waiting for an ePOL, then it executes for a while, and then a syscall happens, that red block, and executes more, and then there's a GC, and everything stops, and then it executes more and does some I/O, and then finally finishes. So you will be able to see this level of granular data. This type of data is good it's hard to digest, but it's important if you have repeating patterns of anomalies. So this sounds good, but how do we do it? Runtime trace package is introducing new APIs, so you can mark sections in the code. Execution tracer is quite expensive, by the way, to keep it running all the time. What we do is we enable it momentarily when there's a problem, and then we disable it again. We collect some data and disable it. And then we are using the execution tracer tool to visualize the output. So there are 3 new concepts being added to the standard library, to the runtime trace package: regions, tasks, and annotations. These are the concepts that allow you to mark sections in the code. The runtime now can associate your code, if you mark them by using these APIs, with its own events. If a runtime event is triggered because of your handler somewhere, it associates them and do the accounting. It can be also used mutually with distributed traces. So you can have a gRPC handler having some latency, and you can momentarily enable the execution tracer and see what actually happened in that handler. The same thing is also true for HTTP handlers and the clients as well. So I said marking sections, and I said we expect you to mark sections. You do it by starting and ending things. We have 2 kinds of markers. The first one is the region, and the second one is task. This is, for example, how you mark a task. The new task is the beginning, and the end is the end of it. You write all the code in between. So I said we have two types. The reason why we have two types is there are some limitations. The other type, region, are the sections of code that cannot span among multiple Go routines. You need to start them on the same Go routine, end it on the same Go routine. And then we have this like logical group, more of like a logical group called task. It just groups them together, visualize them together. It's just like a utility umbrella thing. You usually, for example, if you start a task for an RPC handler, you can see the fine-grained events happening under an RPC. And they are represented as regions. Here you have the task one, and you did some stuff on the region one, which was running on Go routine 1, and then you have the 2 running on Go routine 4, and 3 and 4 and 5 as well. The limitation here is the regions, the green ones, need to start and end at the same Go routine. We currently cannot automatically do association if you start things at a Go routine and end it at a different Go routine. So if you don't know, or if you haven't used the execution tracer, in order to enable the collection, we provide you this super useful endpoint. You can register it on Nmux, and I start a server here at 6060. Then what I'm doing is enabling the collection for 5 seconds and downloading the collected data. Then I can use Go tool trace to visualize it. It starts a web UI if you haven't seen it. I have some screenshots here. So this is one of the new pages added to the UI. In a demo program, I just basically marked all my gRPC handlers, and a middleware. I wrote a middleware that created a task in the beginning of a handler and ended it at the end. So this is what the execution tracer collected for the gRPC Hello World server. If you have seen the example, gRPC Hello World example, this is what it looks like. So Hello World greeter say hello is a handler, and you can see the duration distribution of completed handlers. So it collected 312 tasks because I made only 312 calls. And you can see the latency distribution. So if there are a few 100 millisecond outliers, you can actually click on the links and see what they've been doing. So once clicked, execution tracer will take us to the annotations page, which is again a very ugly page. This is where you see the significant events and annotations. Annotations is kind of like log lines in the lifetime of a task. We can see the RPCs here overlapped with some garbage collection. So it took the task 176, spent some additional time in garbage collection before it's finished. That's why I think it was slightly slower than the others. And each task is made of multiple regions. Can be if you remember the figure I showed before. So in this case, we have 5 regions related to Say Hello RPC, and 1 region related to the runtime, some runtime timers bucket. And again, the distribution is here represented, and you can click on in the distribution bucket and see the details. Things are actually getting more exciting because regions, as I said, supports accounting, so you can tell exactly where the time is spent on. So there's no guesswork. You can see what tweak the latency, and you can optimize things if these are repeating and causing outages. You can see in the first, I cannot see my slide, so it's just not very easy. You can see there's some, scheduler wait for the second row, more than expected maybe, but it gives you very, fine-grained breakdown. So you usually want to collect this data in production because these issues are really hard, capture during development time. You can do it, but the actual case is usually production. But it's as I said, it's extremely expensive. So we recommend turning it on for a while, and getting some data and turn it off again. You can register the existing tracing handler, or you can use the runtime package, runtime trace package to enable and disable it. And once you have the data, you use the trace tool to visualize. So these features are going to be in the upcoming Go release. If you want to give it a try, this is a very good time because Go has now a beta release. You can download it from golang.org/dl, install Go 1.11 beta 1, and it's there. If you want to see an example of how this is useful with distributed traces, I actually added some support to this library, so go get it. Once you create a distributed span, you basically add some regions under it, and then if you enable the tracer, it automatically creates some stuff for the distributed trace, so you can see more granularity under a distributed trace from the data coming from execution tracer. So as I said, nothing is perfect. We have some limitations. The regions need to start and end on the same Go routine, which is not very convenient because we cannot do accounting automatically at this point. So we need to manually mark the code, and this means a lot of work. We're planning to do some manual instrumentation for gRPC in the HTTP package. But if you have custom instrumentation, it means that you have to also do some instrumentation. The other thing is the export format. We currently only export in this format that execution tracer tool can understand. So there's no easy way to attach more data to the distributed traces and maybe modify your visualization you already use for distributed traces to also show this data. There's no plan to work on it, but maybe it might be a future work. But even though the limitations, this is a good addition for people who are using Go in production. We finally can see more, have more visibility into our servers, and can actually can take action when things are going wrong. It was more of guesswork before this tool was available. So I think this is where we are trying to improve, and the future work is very exciting. I just want to questions and comments are welcome. You can also email me. Bugs are also welcome. This is the stage for beta, so try it before 1.11 is cut. Thank you again very much.
So any questions from the audience?
It's not no, it's not a distributed tracing library. The question is this supposed to replace Jaeger or any open tracing or other distributed tracing libraries? It's not distributed tracing, so it doesn't have a concept of propagating, for example, IDs or anything. It's just tracing the things within a process. So it's not, a proper distributed tracing backend or a library. The scope is very small. It's only about understanding the runtime events. There's one more.
Oh, I have a mic.
Oh, there's a mic.
So will it increase the latency of the call? How it analyzes?
Yeah, it actually increases a little bit of the. That's why we don't recommend it. Like to keep it on all the time. It's also the size of the data is just too long. But in that case, you already know that there's a latency issue, and you're trying to more like debug the issue. So you momentarily, for example, you by looking at your distributed traces, you pinpoint, can debug down to a specific server or a specific RPC handler, and from that point on, you only enable the collection for that specific server and momentarily get some data. And the data you collect is probably going to be, the latency will be a little bit different, but it will again give you more idea of what is going on. One more. Are you?
This particular section of code is running, right?
Are you talking about lines or a line in a, for example, a file or something like that?
Yeah, basically in a function I create a section.
Yeah.
And this section could be used by multiple, users. So I don't know which particular call is like a.
You're talking about can we break down the distribution by, for example, a user ID? We currently do not allow you to tag the regions. What you can do is to add some annotations yourself. Annotations is this like logging thing that will be in the, again, in the trace package. You can log the username, for example, and then you can go to the execution tracer and search for that user ID, and then you can catch the task related to that user.
Oh, okay.
Yeah, you need to log and do it manually.
Give it a comment on that, like.
I don't want to give. This is language wars at this point.
I was just curious if you had any comments on your previous experience of working on any.
My previous experience is usually JVM based, so I don't want to. Should I be very like? I don't want to. I don't want to get into the language wars. Not right now. No problem. Thank you.
Thank you for a wonderful talk. So while Chris is setting up, I just want to thank JBD again. That was an amazing talk, and I learned a lot about features in Go 1.11, and hope you all try it out and send bug reports to her. So our next speaker is Chris Lane. He's a Unix Python engineer at PayPal, and now moving from Python to Go. That's what he'll talk about. So.
I guess perhaps I'm leaping into the language wars, but the gist of my talk is if you've used Python, found it to be a productive thing for ad hoc or quickish things, and you're like, oh, Go's really hot now, but like I don't want to get into some big complicated thing. Is this worth learning? Is to say yes, it is. It's got my original background is C. So I do like the efficiency, and I know about arrays of contiguous memory and pointers and that sort of thing. But this has all the modern conveniences. It's fast. It's got a big ecosystem. You can usually get stuff that will interoperate with whatever it is you want to talk to. And so that's the direction of this. So I'm going to start out with two examples of things that are really simple, almost one-liners or whatever in Python, filtering strings and a quick little recursive function to do some JSON editing. Before I dig in, these are some surprises I found coming from Python. The ints are not atomic. I sprinkled my code with, I've now sent this number of bytes. I've made this many connections. And when I turned on the data race thing, those were all flagged because I was just incrementing them all over, and then I had a Go routine to spit them out every minute. The maps are not atomic, which is there are of course concurrent safe maps, but I like the Go spirit of just kind of build your own instead of downloading some module of the week. The nice thing is that these races are really trivial to find. The tooling around Go is super good. And so I just, every time I compile, which is almost every time I save, I run a trace detector and a race detector, and it finds them. Another annoyance that we're having actually more on the PayPal level is there's no standard interface for logging. We're trying to, the PayPal experience with frameworks has been that we just, whatever our intentions are, we end up building like a big monolithic framework where you don't control the execution or the initialization. You're just a little thing down the call track. The initialization is defined. If you want to use one thing to do, say, our logging, you have to buy into the whole picture. That's true with our Python. It's true with our C++, Java, multiple Java frameworks, our Node frameworks now. And so with the Go thing, it's more bottom up, and we're trying to say, how can we make it, here's some cool libraries you can use to make PayPal work easier, but do your own thing, and we'll pass in the handlers that are optional to make this library work better, but if you don't have it, you don't need it. But there's getting everybody to agree on a logging thing is clearly not going to be a given. The other nice surprise is there was no more tuning. The projects I was porting to Go, it was this sort of stupid proxy. It was listening for syslog connections on one side and then teeing it out to a farm of things that then took that message and just put it into Kafka, solely because our weblogs were coming in, for some strange reason, only just 3 TCP connections. So they were not splittable by a load balance or anything. They were just high volume. And also the people that maintained that couldn't upgrade their software, their syslog software, even though there was a native Kafka client for syslog. Anyways, so we had to write this little glue thing. It just listens to syslog and then parses the message and puts it into Kafka, treeing it out. So we got it running on Python, but you had to keep retuning it. We every time the traffic grew up by 25%, you're like looking for hotspots. We switched from pure Python to PyPy, which is a JITting compiler. And so it was, it was just more work than it was really worth. Later on, I'll be talking about more detailed stuff about how to make your thinking work well with what Go offers so that you don't have to worry about the tricky stuff and the runtime just solves the problems for you. Okay, the first little example, we had to drop a lot of URLs that we didn't want to go into the Kafka, different monitoring URLs, URLs we didn't understand, but they were in the logs for whatever reason. So the Python, and this kind of grew incrementally as we found problems. We added them to this, growing list. And it's doing your typical Python thing. If the string is in the data, then just continue a little bit of logging there. There's a split. And Python's really good at that. You can type this in just like as you're thinking what the requirement is. And so this is about 25, 30 lines of code. So this was a rewrite, to be fair. So I knew the problem domain, and so it was easier to structure it. But even with the kind of more explicit and the more type declarations that you need to have in a compiled language, it still ends up being just 24 plus 18, so that's about whatever, 35, 42 or so lines. And you can see it's pretty much the same. You have really nice thing coming from a C background. You have the literal initialization syntax. So if you want an array of strings, you can basically type an array of strings, which I do several times. This is so I switched the Python from just being a list of ifs to a list of strings to check for with constant logic. And then, if string contains, all the kind of stuff that's super easy in Python with string contains and splits and all that stuff is there in Go. It's like Stack Overflow programming where you Google how to do it in Go. This one's a little more fun. This is the sort of thing in Python. It's super fun. It's like a interview question given an arbitrary JSON. I have a list from InfoSec that can only have certain fields in the JSON in my output. And it's a little recursive thing. And a lot of times when people think Go and JSON, they're like, oh, let me tag my structs, and is camel casing this stuff, and I need to know the schema ahead of time. That's good if you're doing an API, or if you're interoperating with a documented API. A lot of stuff is just moving blobs of data around and maybe editing it a bit, and you don't have a schema, and you don't want a schema. So in Python, we have this, it's like I say, an interview type question. You have default parameters in Python. So you initially just pass in a dict and then your list of keys that are okay and how far you've gotten in. You'll notice there's a decorator there, which in our infra is timing it, so you can see randomly we'll get web logs that are like 2 megabytes long or whatever, and so we're on. Oh, look, we took 2 seconds there or something. In fact, for that, we have a maybe sleep. Our Python framework is G-event based, so it's non-blocking I/O and cooperative, somewhat like the Go runtime, but not as good and written in-house mostly. So this is great. It's 22 lines. So again, the Go's somewhere around 45 lines, and it's not as pretty as the Python probably. You have to do more explicit stuff with the types, but Go does do that. It has actually fairly powerful dynamic abilities to introspect types and to do conditional flow based on what type is actually there in the runtime instance. And the cool thing is there's no need to explicitly add in a sleep or even time because the performance is so much higher. It just doesn't even matter. It's never been an instance. And it's a nice recursive thing. There's actually a wrapper function I didn't put here that fills in the default parameters that the Python provides. But that actually means I have a stable API and I can change this if I need to. And it's the same recursive thing. Okay, let's see. Let me go back a little bit and talk about some of the quick and dirty stuff. Or I didn't really write it down, but so it's my job is programming is not really the main thing I do. I'm more advising on decisions and trying to debug things and troubleshoot and that type of stuff. And I program for myself enough that I can be helpful and knowledgeable on the actual details when I'm doing the other stuff. So I need something that's fast development time. If it's a little bit slow, unperformant, I don't really care. That's how I've gotten into doing a lot of Python. And also there's a lot of, I don't know about other places, but there's a lot of Python kind of, under the carpet. When people are just got to get it done, a lot of times they'll put stuff in Python. And of course, as happens, that stuff will grow up and become more critical as people move on. People want that system to keep working and so on. And so there's a need for that kind of language where it's simple, you can do it by yourself, it's quick, it's not surprising. And I think my experience with moving this stuff over is that's definitely something you get with Go. So onto the, so here's the result. So the thing I rewrote, and it took a couple of days of like serious coding, and then like about a week or two of trying to get it to actually build and deploy in our environment, which Go is kind of new, so that was more effort. So in 7 months of running, it has hundreds of thousands of incoming connections. We've only dropped a few dozen, and that was, we had one bad version that had a memory leak, so they exited. The code base ended up being just 2,000 lines of Go, and the original Python was actually longer, 2,600 lines. And that was, the stuff I showed you was a little bit more verbose, but there's a lot of stuff in the Python code from the tuning where like, okay, we need to optimize this hotspot, or we need to add in some more retries here. We need to configure it not to do tuning, or we need to add this configuration in where if this buffer gets too long, then we'll start dropping messages or something. The Go we have it running now on a 16-core machine. It uses every CPU, just really evenly. You watch it under top, and it's just beautiful, and with really no tuning at all for this type of stuff. I like the big numbers. I used to work at America Online, and I kind of got addicted to them. I have this logging going every minute where I increment this stat and print it out. And so one process reports the 61 terabytes of data that's moved through it. No restarts. We don't even have it running under a process restart monitor. It just doesn't go. It doesn't exit. The VM can go bad, but that's okay. The only weird thing, we're dependent on this Kafka publisher library, which is a C library. So the Go runtime, when you call into a C library, that thing will then get a thread until it returns. And so we have kind of an oversubscription on, or we have a large number of Kafka client objects, and then we have, it's like 40 partitions. So there's a fairly large number of network I/O going on there. We do that so that the latency per message on average is low, so that we can keep the throughput high. Because Kafka's, we have it tuned. I think we get an ACK back on one write, which is enough for this, and it's kind of slow. It's in the hundreds of milliseconds, I think. So we have a lot of them, and then we just round robin among them. Or actually, because it's Go, we don't round robin. In Python, it round robined, because that's just the way you have to do stuff. In Go, what we do is we have a bunch of Go routines that are pulling. We have one common channel with all of the messages ready for Kafka going through that. And then we have a bunch of little Go routines, one for each like Kafka client, that just pulls them off. And so whichever one's fastest gets the most work. And then whichever one's slowest just takes its time on that like 2 megabyte message or whatever. And so, but anyways, when there's a network glitch, the Kafka clients kind of freak out a little bit, and it'll bump up to a higher CPU plateau and then never go down. Even when they get up to 100%, everything seems fine. We generally restart them at that point because we get alerts, but there's no functional loss that we've noticed. And then, yeah, so we spent a lot of time writing our Python infrastructure to do this G event and non-blocking stuff, and it's very elegant and so on. And it's about 30,000 lines of code. So that's not part of this project count, and we don't need it. Like the Go just gives you all that stuff. Getting into the two examples that are more in depth. There's and the basic gist for the rest of it is, if you have something where you're doing a lot of locking or doing explicit management of state of something, like a connection pool or a WebSocket state, if you're doing explicit management of the state, that's too hard, and you should rethink it so you understand the data flow and do it using channels and Go routines, and it'll be really nice. So yeah, there's a really good library that will print out if you get deadlocks and stuff, and print out like who has the lock, who wants the lock, what's the last thing that the person with the lock did, and it makes debugging that stuff possible, but it's the wrong path. So yeah, the two things are the connection pooling, and I've done and been fixed and written all kinds of connection pooling. It's kind of tricky. You have to, when you pull it off, you got to see, is it still good, and what are your people pulling off the thread? Are they off of the pool? Are they threads or whatever? And once you get it really good and battle tested under a couple of things, you don't want to touch it anymore. So in Go, it's like a CS 101 exercise. Like connect to a thing, send data, read data, close it. Anybody could write that if you've ever written any network stuff at all. And that to me that shows that it's a language that's just a real sweet spot. It's super efficient. You can use the whole machine. You have access to everything. But the stuff you have to write or you have to depend on people to write is really simple. You don't have to be a genius to write like an efficient handler. It's just simple straight line stuff. And that's for scaling software, that's just such a nice property. Whether you're writing a lot, whether a bunch of people are writing it, the simpler it is, and the better the framework is, so the more powerful that simplicity is, like the happier you will be. So so this was actually a go-to-go rewrite. I was as I was writing this thing, I was going down the path of this connection pool, and here's like my variables. I have a map from like the host name to the connections. I have a mutex for it, and then I have don't actually remember anymore what these are. Oh, it's for round robining. So I'll have like three connections to each named endpoint. And then I had to start adding locks in. I was, by the time this version of the code, I was starting to put some channels in and stuff, and I'm sending the actual connection, net connection through the channel. But it was still had all the locking problems. This is called by that previous one. You can see the round robining logic with like an integer I keep indexing and then taking modulus. This is the thing that actually connects, and this is called getCon, but it can actually fail to return you a connection if it can't connect. It marks that there was an error and then returns you nothing, which is not high availability. Here's now you had to add the con back when you're done. And this is sending the message, so you have to get a connection. You have to handle the case that you didn't get a connection, figure out what to do. You might get more errors here, and then you have to put it back at the end. And then these all are, again, possibly in different Go routines. They're called by other stuff. So it may be the case that there's not even enough locking here. And this is, I was at the point in this code where I'm like, oh, maybe I need this lock, or let me print it all out on paper and draw the locking and try to get a hierarchy of locks or something. And then I watched some Golang videos, and I'm like, oh, wait a minute, let me try this other thing. So my one function that does all that stuff is just, this is 44 lines, and all the state, and this is just the thing that starts it up. So I have a configuration item with how many endpoints I have, and then how many connections on each endpoint. And then the actual thing in the connection pool, if you will, is this function. And it just takes in the endpoint it's connecting to. And again, it's just computer science 101, network programming in Unix. And there's a local variable, local. If it's nil, then this connects. This with, I really like lambdas and that type of thing. So our logging is wrapping this thing. I guess that's also common. So it's wrapping this thing to get our centralized logging, and it just calls get connection. Mm-hmm. Oh, sorry. Okay, sure. So it opens the connection, and then it just pulls the messages off that it's sending. It sends them, it closes the connection, and then loops, and it just keeps doing that forever. And let's see. I will skip then the WebSocket thing. I can give a kind of high-level thing. In the Python implementation, I had a main loop that read all the messages off the socket and handled them, and then one that got calls from the API. This was just a publish sort of thing, and handled and then sent them onto the socket, and it handled reconnection and stuff. And I think because of the G event synchronizing on the I/O, it didn't have any deadlocks. When I just naively transported that into Go, I got into deadlocks both with synchronizing my structures, and it's the sort of thing where you can read a message, and then that means you need to reconnect over here, or it means there's some fatal error on the server, close and reconnect. And I had to, I kept getting into cases where I'm like, oh, I'm trying to close the connection, but I have a lot because I'm really reading from the connection, that type of stuff. So I switched it where all the I/O is just reading off the thing, or if there's and either getting data or an error and putting that into a channel. And then I had one big loop that just read off all the channels. Here's what I've read, here's what I've need to write, and I had a special channel for connect. I need to reconnect. And so that main loop controlled the sequencing. So I didn't get any more deadlocks or protocol deadlocks after that. Okay, does anyone have any questions? Okay, so I just started about 9 months ago, and it's been so I programmed for about 10 years in a place where we had a sort of C event-based networking service, and I really like that. And then I was a stay-at-home parent for a few years, which I recommend. And then I came to PayPal and did some C++ and some Java, and then more and more have been doing Python. But all the stuff I heard about Go is it appeals to that C programmer from the 90s kind of thing. And it was kind of like we were ramping up for the holidays, so the Python was like we either have to go through another round of tuning to make it go up the next 25%, or this Go thing is pretty cool, let me try it. And so yeah, I read watched a couple of videos and read some of the intro to Go's, and then just took this. I had an existing functionality, so it was just porting stuff. The actual coding went really fast. The tools and everything is really excellent. So a couple of months after starting, then it was in production, and I don't even do anything with it anymore. Like the team just restarts it now and then or whatever, adds more logging or something, but yeah.
Thank you, Chris, for giving us, your experience of moving from Python to Go. So we've spaced out our talks. We have mini talks and larger talks, and now we have a mini talk about Go at Netflix. And our last talk, I see some people are, really excited about learning from Bill. He's going to talk about package-oriented design. So stay for that. That's, a fun talk. And Go is, Bill is a very energized teacher. So next is Scott Mansfield he builds distributed caches at Netflix. And he's going to talk about what's happening with Go at Netflix.
Hello, everybody. Awesome. Okay. My name is Scott Mansfield. I'm a distributed database architect or something. We can kind of call ourselves whatever we want, so I figured I'd pick a nice title. I'm here to tell you about what we do with Go at Netflix. It's sort of an overview. It's a short talk, so I'm going to be going through things pretty quickly. If you have other questions about it, my contact info is at the end. I'm going to be posting the slides, and you can talk to me afterwards. Cool. This is just a list of things that we'll be talking about, but we'll move on. This is the high performance data team. It's the team that I work on. We build and run distributed data storage systems. As far as I know, first open source Go project at Netflix and first Go project to actually take real customer traffic has come from our team. That was Rend. It's like a memcached proxy, and we've been using it for so long it's actually already retired. It's still out there. I actually still use it to glue the memcached protocol to other protocols in some places. And we're actually doing new database development as well in Go. Now, I can't really talk to you about it in this venue, but if you talk to me afterwards, I'd be happy to tell you what we're doing. We also are building our own container platform. It's called Titus. This is also open source. If you notice, I'm linking to things on these slides, so whenever you see them later, you can go out and look at them. We have blog posts about most of these things. So we built our own container management platform, similar to the project that was described earlier from PayPal. But it's built to support Netflix, and it's built on top of AWS specifically, so it relies on some AWS features. It's already supporting like the main API layer where all the customer traffic comes in. They're doing great things with decomposing the previously gigantic API layer into a bunch of different like endpoints and containers. It's also supporting all the media encoding that we're doing, all the transcoding, everything, batch workloads, streaming data on Flink, and just plain old microservices. There's an agent and a Mesos executor written in Go to do all the low-level bits for management of the containers, and then it's using some other pieces of the ecosystem. I'm not super familiar with container platforms, but if you talk to me, I'll be happy to connect you with people that are. KS Monkey v2.0 was rewritten to be more maintainable. That was the main motivation, as far as I understand it from talking to the engineer that did it. And it was rewritten in Go in version 2.0. There's a blog post on that as well. It's integrated now into our continuous deployment system so that people can, when they're deploying and making clusters and things, they'll tell it how many things to kill, how often, and you can even turn it off now, which I was kind of surprised that didn't exist in the past, but you can. That's good for test clusters or things like the database systems actually have so many instances that we see a natural failure rate in AWS that's high enough that we don't really need Chaos Monkey. This, I think, is super cool. Faster than light. It's we have our own CDN for people who don't know. It delivers the video to you. It's called Open Connect. And that, since we have points of presence all over the world, we can put proxies on those nodes now and terminate SSL there. We have connections already to the back end through routes that we determine are faster. We can proxy your traffic faster, and it accelerates the whole application experience. And right, this is, I think, a really critical component of this. We actually have a system to allow us to deploy these nodes in places that we don't trust the actual infrastructure it's running on. So we can terminate TLS there without having to be in a trusted site. This, I think, is really cool. There's a lot of promise here. And the last thing I'm going to talk about explicitly is the Netflix Workflow Toolkit, or NEWT. It's a command line tool. It lets you have like this consistent experience between your laptop or your desktop and the CI system, which for us is Jenkins, and set up environments, create new projects. It's like the Swiss Army knife for the developer to allow just easier development experience. So there's also other things that are written in Go. We have somebody from the lab engineering team here who can talk about that. We do CDN, like network management, internal like infrastructure monitoring stuff. I just don't have time to get into all the things that we do. This is all my contact information. If you want, you can tweet at me or email me, or you can look at our tech blog, or we have a job site. Everybody is hiring everywhere. So just all things are hiring. Everybody said. So let me know afterwards if you want to chat. Thank you.
Thank you so much, Scott, for coming. Next up is Bill Kennedy, our beloved teacher from the Go community, talking about package-oriented design and some live coding.
Live coding, because it's not a meetup, it's live coding, right? Yes, that's all. Yeah, woo! I can't use that mic because I got to type. Hopefully my voice is loud enough, and if not, I will. Later. I'm here now, son. Now I gotta get So I wasn't gonna talk about packaging, but what I'm gonna do is we're using live coding. We're gonna show off Tracy a little bit. I don't know enough. Talking about how many people keep Tracy before. Okay, cool. tool profiling. We'll do a little bit of that. I'm assuming everybody here's Good. No. I'm sure. I really want to learn this. Okay, we're good. Okay. As long as everybody can hear me, we're going to be okay. I've been talking all day. So I'm good to try to go. Now? Oh, that's right. You know, there's black all the way around. Okay. Let's get going for a while. All right. Everybody can get code if things good? Fine. So I decided one day I wanted to write a function called find. And what find does is it gets a list of documents, let's say RSSP documents, any number of lists. You can imagine it's a process of a million of these, all this here. But it's going to process n number, making up a million documents. So we've got a collection of documents with file names and a topic that we're looking for. We're just looking for a count. How many times is this topic found across n number of documents? And
You all, the microphone is. Thank you all for coming. I hope you all enjoyed. If you have any feedback on, or any, things that you want to share, please, Slack me, or if you're at PayPal, or send it over Twitter. Also, I am the organizer of Women Who Go South Bay. We do Go Study Nights here at PayPal in collaboration with PayPal Unity. Unity is PayPal's diversity and inclusion group. I love the name because Unity, we're all together in this. And so if you want to sponsor a talk at your company, or if you want to speak at Women Who Go, our next talk is on gRPC. And we actually do live coding, and we work through, doing Java and Go code at the next one. So with that, I will end the night, and we have some t-shirts for the speakers, PayPal t-shirts, so we'll distribute those, and and that's it. Oh yeah, one more thing. We were planning to go to Casino Matrix. Some of us, whoever wants to hang out, to chat later. So I think I heard Bala is paying. so please join us. We're gonna go. It's close by, so we'll all hang out, get beers, and talk about more Go things and South Bay things. So thank you all again.